Good day, everyone. Today we are going to discuss about the vector space. To define a vector space is a set of vectors together with two operations. These operations are the vector addition and scalar multiplication. Talk about addition and multiplication. This means that there is an adding and multiplying involved. These operations must follow specific rules known as axioms. So, although it is about adding and multiplying, there must be a specific rules to follow, meaning to say we cannot add or multiply that is out of the rule. There must be an axiom or the rules that we need to follow in order for us to apply the operations. Okay, so next. In vector addition, we add corresponding components. For example here, 2 and 3 are the components of the vector, and 1 and 4 are just the components of the another vector. So when we add them together, all we just need to do is to add its corresponding components. So the corresponding component of 2, that is 1. So when we add them together, that is 3 basically. And the corresponding component of 3, that is 4. So 3 plus 4, that is 7. Meaning to say, when we add these vectors, we just get another vector in our vector space. As for in scalar multiplication, we multiply each component by a scalar. For example, 2 here is our scalar and the 3 and 4 are the component of the vector. What we are going to do here is just to simply multiply them distributively. So 2 times 3, that is 6, and 2 times 4, that is 8. And this answer is just another vector in the vector space. These operations must satisfy certain properties. That is how we start a vector space. We first apply the operations before we go to its properties or applying its axioms. And for the next slide, we are going to apply it with our 10 axioms. So these are the axioms for our vector space. By the way, the first 5 axioms are related to addition, and the second 5 axioms are related to scalar multiplication. We have here a vector space over a field F is a non-empty set of elements V, together with two operations. Basically, these are the symbols for or the operations that we are going to use. This is for addition and for the scalar multiplication, which will satisfy the following axioms. Here let x, y, and z be in V and 1 c and d base scalars. Then, the first one is the closedness. We need to say when we add the components of the vectors x and y, its answer is just another vector in the vector space. For number 2, this is commutativity, meaning to say when we add the components of x and y, it's just the same as adding the components of y and x. This means that order doesn't matter. X plus y is just exactly the same as y plus x. For number 3, this is about associativity. We need to say this parenthesis doesn't matter because when we add the sum of x and z to the x, it's just exactly the same as adding the sum of x and y to the z. So meaning to say, really, that parenthesis do not matter. For number 4, this is about the zero vector rather. There exists a zero vector in V such that 0 plus x is equal to itself for any x in V. And of course, the 0 is a vector in a vector space. So when we add 0 to any of the vector, its answer will be itself. Example here, 0 plus the vector x is just the same as x for any x and V. For number 5, this is about for each x and v, there is a unique element negative x such that x plus negative x is 0. This is also about the negative vector, meaning to say for each vector in the vector space, there is a unique element or it's negative, which is here a negative x such that when we add that vector to its unique element which is in negative, then its answer is 0. So That is all about the five axioms related to addition. The next one are the five axioms related to the scalar multiplication. So the first one is the closedness, meaning to say when we multiply c times x, the product is still another vector in the vector space. The seventh axiom is about the distributivity of a scalar multiplication, meaning to say we are going to multiply c to the sum of x and y, and that is exactly the same as c times x plus c times y. The eighth axiom, this is about the distributivity of a scalar addition, meaning to say the sum of c and d will be multiplied to x, and that is exactly the same as c times x plus d times x. So we have just simply distributed c and x, and then we add d times x. For our ninth axiom, this is associativity, meaning to say parentheses do not matter. Here, c times d times x is just the same as c d or c times d times x. Our number 10 is, or our 10th axiom, this is about the unit element, meaning to say when we multiply 1 to the x arbitrary v, it's just itself. So that concludes our axioms for both addition and scalar multiplication. Now let us going to apply these axioms, having vectors with their components. Example, let V be the set of all ordered pairs in the Cartesian plane, R squared and F, the set of real numbers, where the operations are defined as follows. So this is for the operation addition. Just like earlier, we have just added the corresponding components. The component of x sub 1 is y sub 1, so we add them together, and x sub 2 and y sub 2. And for the scalar multiplication, we have just multiplied the scalar to the component of the vector. And the answer is cx sub 1 and cx sub 2. Here we have our proof. Let x be x sub 1 and y sub 1 and y be y sub 1 and y sub 2 and z with the components z sub 1 and z sub 2 and cd be real numbers. Then, applying the first one, which is the closedness, we are just going to simply add the components of x and y. And we know that when we add them together, we will just simply add the corresponding components. So the corresponding component of x sub 1 is y sub 1, so we add them together here. And the corresponding component of x sub 2 is y sub 2. And we have just got another ordered pair. Number 2 is what we called as the commutativity, meaning to say order doesn't matter. So we are going to add the components of x and y. So the components of x are x sub 1 and y sub 2, and the components of y are y sub 1 and y sub 2. So adding them together, we have obtained x sub 1, y sub 1, and x sub 2 plus y sub 2. And this is exactly the same as y sub 1 plus x sub 1 and y sub 2 plus x sub 2. And this satisfies y plus x, since we have just kinda interchange the order, which satisfies the commutativity axiom. Number 3, this is what we call as the associativity, meaning to say parentheses doesn't matter. So here we add x to the sum of y and z. We have here x sub 1 and x sub 2 as the components of x, and y sub 1 and y sub 2 as the components of y, and z sub 1 and z sub 2 as components of z. So applying associativity, we have obtained, these are the process, you can check that. And applying associativity, we have obtained x sub 1, x sub 2 plus y sub 1, y sub 2 plus z sub 1, z sub 2. And that is exactly the same as here, x plus y plus z, which satisfy our associativity axiom. Number 4, which is about the zero vector. So when we add the vector to 0, then the answer will be just itself. Number 5, this is about the zero vector, or the negative vector rather. This is negative vector rather. That for any element of x, then there exists, it's negative. So let negative x has the components of negative x sub 1 and x sub 2. And of course, then we add them together to the x, which are x sub 1 and x sub 2. So the answer is just 0 and 0, which is 0. Next, we are now in our scalar multiplication. So applying it with the components c times x. So c times the components of x, which are x sub 1 and x sub 2. It's just cx sub 1 and cx sub 2. And this is an ordered pair. Seventh axiom, this is about the distributivity of a scalar multiplication. Meaning to say, when we multiply c to the sum of x plus y, it's just the same as c times x plus c times y. So these are the process. You can check that. Number 8 is, this is about the distributivity of scalar addition, meaning to say the sum of c and d will be multiplied to x, and that is exactly the same as c times x plus c times y. So here we have simplified x with their components x sub 1 and x sub 2. So that will be equal to c plus c times 1 and c plus c times 2, and that would be equal to cx sub 1 plus dx sub 1 and cx sub 1 plus dx sub 2, and that would be equal to cx sub 1 and cx sub 2 plus dx sub 1 and dx sub 2. And to expound them, to obtain the answer, that would be c times x sub 1 and x sub 2 plus d times x sub 1 and d x sub 2. So simplifying them together, since these ones are just the components of x, and thus we have obtained c times x is plus d times x. So we have figured out that this one here are just exactly the same as this one here. So for our 9 axiom, this is about associativity, meaning to say when we multiply c times d times x, it's just exactly the same as c times d times x. So this is the process in obtaining c times d times x. And for our number 10, this is about, again, the unit element, which means that when we multiply x arbitrary to the v to 1, the answer will just be itself. But first, we will define x, which have the components of x sub 1 and x sub 2 multiplied to 1. That is 1x sub 1 and 1x sub 2. And that is the same as x sub 1 and x sub 2, which define the x. And that concludes our examples. Moving on, let us have another example. Verify in detail that R to the third is a vector space. The process goes like this. To verify that R to the third is a vector space, we will check all 10 vector space axioms under the usual operations, which are the addition and scalar multiplication. So we all know that in the vector addition, we will just simply add the corresponding components of the vector. So x sub 1 having the corresponding component of x sub 2, so we add them, that is x sub 1 plus x sub 2, and y sub 1 corresponding to y sub 2, and it gives us y sub 1 plus y sub 2, and z sub 1 corresponding to z sub 2, it gives us z sub 1 plus z sub 2. So applying the vector addition, this is the result. And now moving on to the scalar multiplication, we will just simply multiply c to the components. And what we are going to do here is we will just distribute the scalar to each of the components. And it gives us c times cx, cy, and cz. So this is the first process. And now moving on, let u be the x sub 1, y sub 1, and z sub 1. Our v be x sub 2, y sub 2, and z sub 2. And our w be x sub 3, y sub 3, and z sub 3. And cd be real numbers. So the first axiom, which is the closure under addition, meaning to say when we add u and v, this will be another element in the vector. So u here and v, adding the corresponding components, it gives us x sub 1 plus x sub 2 and y sub 1 plus y sub 2 and z sub 1 plus z sub 2. For the commutativity of addition, we will just simply show that u plus v is just exactly the same as v plus u. So this means that order does not matter. So applying the commutativity of addition, rather, it gives us x sub 1 plus x sub 2 and y sub 1 plus y sub 2 and z sub 1 plus z sub 2, which is exactly the same as x sub 2 plus x sub 1 and y sub 2 plus y sub 1 and z sub 2 plus z sub 1. Moving on to our third axiom, which is the associativity of addition, meaning to say the parentheses do not matter. So when we add u plus v, the sum will be added to w. So applying them together with their components, it gives us x sub 1 plus x sub 2 and y sub 1 plus y sub 2 and z sub 1 plus z sub 2 plus the w, which is x sub 3 plus y sub 3 plus z sub 3. And this, our answer under this addition. It gives us x sub 1 plus x sub 2 plus x sub 3 and x sub 1 plus y sub 2 and y sub 3 and z sub 1 plus z sub 2 plus z sub 3, which is exactly the same as u plus v plus w, which when we see the process, although this have kind of different from the other one, but still it gives us the same result. So it shows that the associativity of addition is true. Axiom 4 is the existence of zero vector. So let us define zero because having the components of 0, 0, 0. So we know that our U has the components of x sub 1, y sub 1, and z sub 1. So each components will be added to 0, and that is exactly the same as the U. That is exactly the same as U. I get it. So our fifth axiom is the existence of additive inverse, meaning to say there is a negative vector. So for every negative u, there is components that are negative. So u plus negative u, it gives us all 0. So in the process here, there is negative x sub 1 plus x sub 1 and negative y plus 1 plus y sub 1 and negative z sub 1 plus z sub 1. And the answer is 0. Number 6, which is under the scalar multiplication or the closure under scalar multiplication. So as defined earlier, Cu equals Cx sub 1 times Cy sub 1 and Cz sub 1. This is the process of the scalar multiplication. This is just the same as what we have introduced earlier. And this ordered pair is just another or still another vector in the vector space. Number 7 is the distributive property or scalar over vector addition. So we will just simply multiply the c to the sum of u and v. And it gives us the answer cx sub 1 plus cx sub 2, cy sub 1 plus cy sub 2, cz sub 1 plus cz sub 2. So the process goes like this. Multiplying c to the elements or the components of the u and the v. Axiom 8 is the distributive property under scalar addition, meaning to say, or the distribute property, or what we call as the scalar addition rather. So first, we will sum up c and d, and then we'll multiply them to u. So distribute the following, since we have already expounded it all together. C plus d to the components of u, which are x sub 1, y sub 1, and z sub 1. And Distributing them together, c plus d times x sub 1, that is cx sub 1 plus dx sub 1, and c plus d times y sub 1, that is cy sub 1 and dy sub 1, and c plus d times d sub 1, that is cz sub 1 and dz sub 1 rather. And to group them all together according to according to the process, it gives us cu plus du. That is how it works. Axiom 9 is again the associativity of scalar multiplication, meaning to say, again, the parenthesis doesn't matter. C times du is just exactly the same as CD times u. These are, we define d times u here, that is c dx sub 1, c dy sub 1, and c dz sub 1. And as for the cd times u, which gives us the same answer from here, which is c dx sub 1 and c dy sub 1 and c dz sub 1. So it means that the axiom number 9 shows that R to the third can be proven as a vector space. The last one is our axiom number 10, which is the identity element of scalar multiplication. So again, from what we have discussed earlier, axiom 10 is about identity element. Meaning to say, when we multiply 1 to the u arbitrary to v or to the vector, the answer will always be the same. The answer will be just u. So simplifying them together or expounding them, that gives us 1x sub 1 and 1y sub 1 and 1z sub 1, which is exactly the same as x sub 1, y sub 1, and z sub 1. And there it leads us to the answer, which is still u. And that con and all axioms are satisfied from first to last, and therefore R to the third is a vector space. So we will know that the given is a vector space when the 10 axioms are satisfied. When either of the axioms cannot be satisfied, then it is not a vector space. And that concludes our discussion about the vector space today. Thank you so much for your listening. God bless.